Let's come back. I invite Professor Airton. Professor Airton is a professor at Univap, University of do Vale do Paraíba. His expertise is in spectroscopy, Raman spectroscopy, infrared spectroscopy, optical biopsies, X-ray fluorescence and dentistry, and in case Raman spectroscopy in different fields of pharmaceutical and cosmetic products and cancer. I think is.
How about now? Great. Well, that's the first time that I use that, so I'm not quite comfortable. Anyway, first of all, I'd like to thank the organizer this opportunity to be here and oh, that's strange, and talk a little bit about what you have done in our laboratory, in our institute. So Univap is a university that is not far from São Carlos. It's located, it's about 3 hours traveling from here, and is located between Rio de Janeiro and São Paulo. It's a very nice place where you are very close to the beach and also very near to the mountains. So that's, this is the institute where all the research in this university is performed. And this is the place where we are, and that's the technological park that we have to do the interaction between university and transform our research in a product. Well, to outline my talk, I would like to start it with a brief introduction about Raman spectroscopy. And then I go to say a little bit about the Raman instrumentation and include some technical aspects of this instrumentation. Then introduction into Raman and to infrared spectroscopy. Again, a little bit about what is in the field today in terms of instruments. And then I jump to the biomedical application using those Raman and infrared, mid-infrared for the biomedical field. So starting with the history or story of Raman. Okay, this when the light interacted with the matter, it is scattered, and this scatter of light, it could be elastic or inelastic. The inelastic scattering was predicted by Michelson long ago, on 1923, but this effect was first observed by Raman on 1928 when he wrote this paper to Nature. The whole story started when he was traveling to Europe, and he started to observe the colors change in the sea. And when he went back to India, he performed this experiment using this very advanced instrument on that time, and he could see that when you shed the light in a liquid or gas, you have inelastic scattering of this light. And for that, he won the Nobel Prize on 1930. Okay? So the Raman effect is then the inelastic scattering of the light. But when you shine the light, let's say laser line, to your sample, to your tissue, or any matter that you want to study, what you have first is the most strong effect, is the elastic scattering. The elastic scattering means there is no shift in the frequency. The same energy you send it, the same energy you receive it back. And that is very strong. For you have an idea, it's about 10 to minus 5. But the elastic scattering is not important because it does not interact with the bounds of your tissue, of your molecules. So what is most important that could bring information for the bound of your molecules is the inelastic scattering, because then you have this interaction. And when you have this interaction, it will depend the state of your molecules. If in the ground state, you have the Stokes scattering, and if it's in the excited state, you have the anti-Stokes scattering. by the Bose-Einstein distribution, you can guess that the unstoked signal is much weaker than the stoked ones. So usually, what we study or what we analyze when you shine the light is the stoked side. Although there are some experiments where you could collect simultaneously the unstoked and the stoked signal, and from that you could determine the temperature of your sample. Okay, so what we're going to present then is the stoked study of those tissues. So the Raman effect is mainly based on the change of the polarizability of the molecules. When you shine the light, you have an electrical wave, and this electrical wave changes the polarizability of your molecules, for instance, and that induces this dipole moment. And this dipole moment will depend, in fact, the ability to split it, the charges of your molecules. And that comes out then the Raman equation, I mean the change in the polarizability. When you see this equation, you have three terms there. The first one corresponds to the most strong one, that is the Rayleigh scattering, elastic scattering. Then the second one is the unstoked, and the third one is the Stokes Raman. So that is what we are looking for. And here is a simulation from what happened here when you shine a laser line in your sample. So when you analyze your data in the Raman, you in the x, you have this Raman shift. What means Raman shift is that the energy that you detect, or the frequency of the vibrational mode, does not depend of the laser line. So no matter which laser line you are using, what you see here is the shift for comparing to the excitation line that you are using. So if this mode, let's say here, it's about 1450 wave numbers away from the laser line, if you change your laser line, go to 514, it's still the same frequency, the same vibrational, okay? So the Raman does not depend of the laser line. And usually different from the infrared, since it's a Raman shift, you represent this as a reciprocal centimeter on the xi axis. So when you look at then the Raman, what you see is exactly like this. Is the vibration is phonons, is the vibration of the lattice, or the vibration of the molecules. So you can see there, depending if it's a symmetric or asymmetric vibration, you're going to have different vibrational frequencies. And from that, you could identify your sample. How come? By less dynamic calculation or any first principle calculation. Once you know the mass, once you know the bounds of these molecules, you could determine what's the frequency of what's the vibrational frequency. That's why Raman is called as a fingerprint techniques. So it's to have a brief idea. So each of those bounds here, you have a different vibrational frequencies. Okay, so that's basically given by this equation: greater the mass, less for the frequency. So from that, you could determine those are the most important bounds that you have in a biological tissue, for instance. So you could determine, based on that, what's the vibrational modes that you have in your Raman spectra for the tissue. So what is used nowadays for this, to do this type of measurements? So for Raman, you need a laser, a monochromatic light. Okay, nowadays use these diode lasers that is quite cheap, $6,000 you buy a good laser, okay, with a good line width. You need a lens, and you need a notch filter if you have here a spectrograph that is a monochromator. So it depends how much you want to get rid of the scattering light. Don't forget that when you are shining your sample here, the light that is scattered is the elastic scattering and the inelastic scattering. So for get rid of this elastic scattering, use here a notch filter that is going to block the elastic or the frequency of the laser that you are exciting your sample. So once you block this light, what goes through is only the inelastic scattering that goes to this your spectrograph. On this spectrograph, you have a grating in a dispersive system where this grating will disperse this light here, and only the rest, because this notch filter is not, the optical density is not 100%, so some elastic light goes through. So we have to get rid of it using a grating, for instance. It depends how strong is that. You can use a simple monochromator, double, triple. It depends how close you want to get to the laser line. If you have a vibrational mode that is only 15 wave numbers from the reciprocal wave numbers from the laser line, you should eliminate the laser as much you can. So you have to go for the triple monochromator or spectrograph. Or if you want to go like in biological tissues, that's the vibrational modes that's more important, is over like 400. You can use a simple monochromator with a notch filter here, and you are in the job. You can do this type of research and diagnosis, and it's much cheaper than a triple monochromator. And besides that, all the systems could be coupled to the optical fiber. So you could perform in vivo analysis using Raman. What would be the main advantage to use Raman for that? First of all, you are using optical fiber, so there is no invasive techniques. Second point is real time. Once you shine the light, you collect the scattering light, and then you have your diagnosis right away. So you don't have to remove the sample, you don't have to do biopsy, and then you have a real-time diagnosis. So that's the main advantage to use Raman. And Raman, as you see, is very specific to the vibrational modes. The other type of instrument that comes to the late of 80 is a FT-Raman. In the beginning, FT-Raman were used for biological tissues because it could suppress the fluorescence. It could suppress the fluorescence because you are using here a 1064 nanometer wave numbers. So we don't have energy enough to excite the electronic states of the fluorescence. But the main advantages of using FT-Raman, it's using a Michelson interferometer. The main advantage to use FT-Raman is internal frequency calibration, intensity calibration, but from my point of view, is this multiplex advantage. Different from what is a dispersive system, with FT-Raman, you could collect the Raman signal from, let's say, the whole unstoke and unstoke vibrational modes without not needed to change the grating. When you have a dispersive system, you have the grooves of this grating, and then depends what is the region you want to collect it, you have to change this grating to cover that spectral window. With FT-Raman, you don't need to do that. It collects the whole set of vibrational modes of data in one shot. And also is a large light collection capability. The advantage of it, the first one is the Raman efficiency. It goes 1 over lambda 4. Means that the intensity of my Raman signal, now instead to use here, let's say 785 nanometer as a laser excitation, I'm using now a 1064. Means that my intensity now will drop quite fast. Dividing this by 1064, dividing that by 785, I drop my intensity. So to do that, to compensate that, I have to or increase the power or increase the integration time. Means that I need more time to collect the spectra. So it depends of your application. If it's an in vivo application, you cannot sit with the optical fiber, let's say on this, like in this mouse, for 30 minutes in the same spot to do this diagnosis and also is not real time, no longer real time, okay? And the main reason for that, because instead to use a CCD detector, that I forgot to mention on the previous slide, a charge cup device, we are using here now a germanium or a InGas detector. And the point is, although it has a very nice quant efficiency for this wave number, the electronic noise is quite high. So I need more integration time to get a better signal-noise ratio, okay? So that's the main advantage. So it depends what you are doing and what you want to do. So what is the main enemy, I would call like that, Raman, is the fluorescence. And why is that? The fluorescence has a much stronger signal than Raman. So what happened then if I'm probing biological tissue with no confocal, of course, biological tissue with a 514 or 532 nanometer laser line? I have excited these electronic states, and my fluorescence, you mask all the Raman signal that I have it. So that is not good. So what I have to do then, when I have some samples that has this fluorophorus, is going to have fluorescence, I have to increase the laser line, the laser length, the wavelength. But when I increase the laser wavelength, I decrease my cross-section of Raman. It goes 1/λ4. So basically that is what happened. That's a sample, I think it is a chocolate spectra. I'm a fan of chocolate, so I collect that spectra to see. And this is with a 785. The up part of this spectra is collected 785 nanometer laser line in a dispersive system. And the blue one is using this FT Raman with the 1064. So clear, what you see here is a broad peak of fluorescence. You see very tiny shoulders here that represent these modes, the water mode, old age mode here, for instance. So it's quite impossible for you analyze this type of data using 785. So the fluorescence is so high that you mask your Raman modes. So that is not so good. So you have to have a balance to do that. One option to avoid this fluorescence, I think Professor Brian mentioned that, is using surface enhancement Raman spectroscopy. In the surface enhancement Raman spectroscopy, what you're going to increase is the Raman modes intensity, not the fluorescence. So that's one option that you could avoid the fluorescence. Another one is shine the laser in your sample and quench this fluorescence, but sometimes works, sometimes doesn't work. Another option is to use what you call source. That means a surface shift of the Raman laser line. You collect a spectra with using 785, and then you make a drift in the laser line to 785.2, collect again the spectra in the same spot, and then we're going to have two Raman spectra shifted by 0.2 nanometer, but the fluorescence signal will be the same. Then you have to do is subtract this fluorescence and then integrate the spectra, and then you have back your spectra. So that is also one option to avoid the fluorescence. So what you have to have in mind then when you're going to choose your laser line is what sample you have it. How strong your Raman signal. It's a balance. Okay, so don't forget that the intensity is 1/λ4. So depends what you want to use it. There are plenty of laser lines available in the market, and it depends now your application. Always bear in mind this factor and that factor. Do not excite the electronic states, otherwise you have a fluorescence. Okay, or then you could go to confocal Raman or different techniques to avoid this fluorescence. Talking about confocal Raman, the confocal microscope could be coupled to the Raman for in vivo or for in vitro measurements. And basically what it does, it just probe the laser spot that goes direct to your detector. All the other scattering light are blocked by this pinhole here. So what is good on that? You are probing a tiny part of your sample, and means that the fluorescence you decrease because you are not probing the whole set of it, not the bulk. So it depends now what you want to do and the type of application you want to use it, because it depends of the lateral and also the axial resolution. So if you want to do some image using your confocal Raman, you have to know what resolution you needed, and depends also your application. If you want to do like in vivo analysis, you have to know how deep it goes, okay? And to do this, it's important the axial resolution. If you want to probe, let's say, with a confocal Raman a skin, how much resolution you need. So is a 2 micron enough for detect the fact that you want to see it? 4 micron, so it depends of your application. But that's a good approach also to eliminate the fluorescence. So what you have nowadays in the market for ex vivo or in vivo application in terms of confocal microscope. The VTEX system, Alpha 300, is a good system for you have an idea when you do image of your sample. Let's say that you have a biological tissue, you make a slice of this biological tissue, and then you want to image it. When you're going to image this slice, you cannot stain it with HA, with any other chemical, because Raman is sensitive to any vibration. So it have to be just a slice of the sample in a window that is not Raman active, okay? So when you place the slice here, it could collect the image in a 3D way in a very fast approach. Let's say that this example here, using this 250 pixel, that's the size of the CCD, we could collect this 62,500 spectra in 1 minute. So it means that he could map a large area in a very fast way. Another system that you have it is this from Oriba, that also it can probe an image with the same approach, but not so fast like a VTEX system. Okay, it's a little bit slower. So those two are used for in vitro application. If you want to do in vivo application, let's say that you want to study, you are in a pharmaceutical, or you are in a cosmetic industry, or even you want to probe some nanoparticles that go deeper in the skin to do a PDT, for instance. So you wanted to determine how deep your nanoparticle goes, or how deep your active goes, and what is the effect of it. So you have to use this type of system. That's the Rivers system, the Holland company that built this system specifically to measure skins. So nowadays, that's na verdade, is a new technique in the cosmetic field. Before, people has to do biopsy, corneometry, many different techniques to see the hydration, NMF content in the skin. And nowadays, this can be done from the surface of just place your arm here, your neck, whatever you want to measure, your hair. And then you can collect the Raman data from 0 to 200 micrometer deep in about 5 to 10 minutes in a good signal-noise ratio. The spatial resolution of this system is about 2 micrometer. So you could probe, you could place a mouse, rat here inside, on the top, animals, whatever you wanted. That's what you do in the lab. We change the window for animal model, and then we place the window for human beings. So we do this type of study for the pharmaceutical industry, cosmetic industry, and also using animal model for a PDT and cancer death and diagnosis. It's a good system. So that's a typical Raman spectra. That's my skin. Okay. So that's a typical Raman spectra of my skin. From your skin, it'll be quite the same. So I have here all the vibrational, we call each peak of that the vibrational modes. So I have here the whole set of amida 1, amida 3, means collagen. Okay. So I can probe collagen, protein, lipids. I can see anything that is Raman active in a nice spectra like that. This is about 5 to 10 second spectra that is collected in vivo. Okay? The assignment of those bands could be found on those two papers. There are some typo on this paper here, but the rest is quite fine. So you could identify any vibrational modes using those previous publications, doing dynamic first principle calculation if you are a theoretician, but that is mainly what you have it. And based on this, it's quite nice now to use Raman for diagnosis. You see, it's very specific. So if you have a disease, the disease, what comes with the disease is exactly the change in a molecular bounded. And when you change this molecular bounded, you're going to have it changed on these vibrational modes, because that's what you're measuring it. So that's the whole principle to use Raman for diagnosis. You could determine what type of cancer, if the tissue has a cancer, benign or malignant, only looking what is the intensity and the shift of the Raman spectra. So that's the whole process to use Raman for in vivo real-time diagnosis. How about infrared? How infrared comes through? Okay, that's a little bit older than Raman. Right? This is in 1800. This guy, William Herschel, he was shining the light, and then he realized that in a part of the spectra where he didn't see any light, he could detect that there is increase of temperature on that region. And then he performed some more studies, and he found that there is some light here, but we cannot see, and that was called then infrared light. So that's the infrared light is the light that we use it to study these vibrational modes on those samples. And you are near to the visible, and in between visible and microwave. So you have near infrared, mid infrared, and far infrared. So it depends what you want to measure it. You have to choose your source. You have to choose your detector to probe different spectral region of your infrared. Different from what is Raman is scattering of the light. Infrared is absorption of the light. Okay? So it depends there. You have in the Raman, you have a monochromatic light, a laser line. Here you have a source that has emission in a very different wave numbers, because you're looking different absorption lines. And the absorption will occur when you have the same energy from the laser for the light that's coming through. Okay? Then you have the absorption effect. So basically, this system has the same principle from the FT Raman. It has a Michelson interferometer. So you have a fixed mirror, a beam splitter, and a mirror that translated from one side to the other side. And then when the light is shining on that, you have a constructive and destructive interference. And that is reconstructed for your whole spectra later on. So this source, for instance, this ETC Everglobe is from, I don't know, maybe from Nicolet. I just got an example. It could probe vibrational modes, get from 20 to 9,600. If you want to go higher than that, you have to choose different source. And detector is the same. Depends from the energy that you want to detect it, you have to choose your detector. So there are a plant, that's the most common detector, that the DLTGS, that covers from 350 wave numbers to 2,500, or MCT. That's a bit higher than this DTGS. If you are looking for vibrational modes very near to the limit, very low wave number, you have to use the bolometers. In biological tissue, that's more than enough. DTGS or MCT detectors are the most common ones that are used nowadays. So the basic principle of FT infrared, you collected the spectra with no sample, that's your background, and then you collect the spectra from your sample. And then when you have those two spectra, the background and from your sample, you do this integration, and then you have your pure spectra. So that's the way that infrared works, different from Raman. Okay, there you don't need to have your reference spectra. So that's the typical infrared spectra from some biomolecules. You have lipids with these vibrational modes, with these wave numbers, collagen, proteins, with this quite different from what we have in lipids, DNA, and also mucin. So again, they have your fingerprint. Once you know the vibrational modes, you identify your sample. Okay, there is no mistake to that. And that's the typical infrared spectra from a microorganism, let's say. So in the infrared, it's quite used to calculate the first or the second derivative of the spectra, and then you really could determine the peaks on this spectra here. And at the end, I'm going to ask you, what is the vibrational modes of amide-1? So you have to keep in mind this whole table, okay? Just kidding, that's not exam in the end, okay? So that is only for you know that that exists, and then once you get through to this type of study or search, you have to associate what's the vibrational modes that you have founded and from what has previously published. And this is a typical spectra from infrared and Raman for 3 different samples. So you have the hamster brain, the bacterium, and the fluid. So what you could see when you compare what is the Raman scattering and what is the infrared, you see that what is more intense in infrared is less intense in Raman, and vice versa. Why is that? Raman is scattering of the light. Infrared is absorption of the light. So what is scattered is not observed, and what's observed is not scattered. So means that those two techniques are complementary. So if you want to know the whole set of vibrational modes on your sample, you should use those two and combine those two techniques. So that shows more or less for the same sample what is Raman and what is infrared. So far, so good. Anyone with the face that I don't know what this guy is talking about? No expression for that? Okay, let's keep going then. So that's why we say that Raman is a fingerprint of your sample. Usually when you do Raman, you're going to find a fingerprint. So that is the techniques. That's Raman and also infrared. Okay? So you could probe anything that you have that is Raman or infrared active. And the activity of Raman or infrared modes, you depend from some another physics that is not the topic of this talk today. So now you imagine, you have a plant. On that example that I show you for the Raman, this guy had about 62,000 spectra. So you're going to spend your whole life to analyze it one by one, right? That's for a single image of a slice. So means that you're going to spend your master program, your PhD, and maybe you finish after your postdoc. So that's not worse. So what people use then is some statistic modeling to treat this data. So once you have these tons of Raman spectra or infrared spectra, you have to compress your data. You have to analyze what is more important, because that's what you want to differentiate it, if you want to do diagnosis, for instance. Okay? So usually they use factor analysis, cluster analysis, or artificial neural network. So when you do factor analysis, so if you have a bunch of data, it will extract what is the most important ones. And then based on this difference, you could reduce drastically the amount of data that you have. Or then you could use also cluster analysis. With the cluster analysis, also is an unsupervised classification test, means you plot it on the program, and it does classify. You have no control of that. The only control you have it is to choose what spectral region you want to analyze. Because sometimes, depends on the disease or the things that you want to analyze it, you don't need to place the whole spectra. You just get region of the spectra, what is the most important that you could see any variation by eyes. So you reduce drastically the amount of work. Or then you could use artificial neural network, where the artificial neural network is a supervisionized classification. Means that you have to train, it's like the brain. You have to train your data. So you get a bunch of data and then say, okay, all the data that appears like that is benign. All the other ones is malignant. And then to validate this, you do cross-validation. You take one data out, put it back in the system, see if he could classify. And then you keep doing, without overtraining your set. That's essential. Okay. So those three techniques are used nowadays quite commonly to analyze the Raman or infrared data. Any program that comes with those instruments, Renshaw, Brooker, Opus is Brooker, Oriba LabSpec, it comes with this statistical analysis, because they know that this should be done, that should be used. So the factor analysis then works like this. I have a bunch of spectra, 3,500 spectra here. I want to see what's going to happen. So the first thing that's important, once you get your spectra, is to see the quality of your spectra. If there are like CO2 contamination in the room, water contamination, you have to normalize your data. So you have to do a pre-processing before. Otherwise, you're going to have misclassification later on. And this is not related to the disease or any other things, but because the quality of your spectra were not so good. So you have to do the pre-processing. Once you do this normalization, smoothing, whatever, it don't destroy your modes, right? And don't do like 20-point smoothing. Do 3, 4, 8, subtract your background. You do this. I'm run out of battery. You run, not me, but laser. And then you do the PCA. I still have more battery, more energy. And then you have this spectra. When you do this PCA, principal component analysis, what it does, you have to center your data, and then it's going to identify what is the most relevant difference between one set, what is the second PC is what is not so relevant as in the first one, the third, and so on and so forth. So you have to, of course, if you go to the 20, what you call principal component, you're going to end up to analyze the noise or the fluctuation. So you have to be careful, because PC1, 2, or 3 already contain about 99% of the spectral information. So you stop in the PC1, 2, or 3, okay? And then once you do it, you put it in the scattering plot, and then you could classify. Each point of that means that is one spectra that comes from here. So you have your classification. Let's say this is a strain in bacteria, gram-negative and gram-positive. And that is the scattering plot. So that is one type of approach that we use in the infrared, or use this in Raman as well. The second approach is cluster analysis. The cluster analysis is important, depends, of course, from all the study you have done. Let's say that you want to use it, you collect 100 spectra, not image, 100 or image also too, yeah. But let's say another example. You collect 100 spectra from people, and then you want to see the effect of aging on his skin. Okay, I want to see people that I get 4 different groups of aging, and I want to see what is the effect of, let's say, the aging process. So what I have to do then is using this cluster analysis, and what I expect then is once I do my cluster analysis, I'm going to group it in 4 different groups. Each group comes with different age. Okay, so you end up then with things that is calling like a dendrogram, where each of those groups belongs, each of that person belongs to that group. If I do this in an imaging of a skin, for instance, not a skin, sorry, come back to the tissue. Let's say I want to probe a thyroid tissue, and then I know that I have those morphological cryptas, and not colons a crypta. I'm a physicist, so that's a good point that Katarina said, that everyone has to stick on their field. So I'm a physicist, but I know that in a colon tissue there are some crypts that they call. So you have the spectra from that crypt. So what are you going to do once you collect a bunch of spectra? You're going to have clusters for each of these morphological from your sample. Then you could identify, and then you could classify it. And then once you do it, you could reconstruct your imaging, and then replace that by your eyes. So that's the whole process of cluster analysis. And what is in the market today for the infrared? A Bruker one. That is the quite good system. It has a detector size with a 250 by 250 square micrometer. It's a good system for imaging. Then the second one is a Perkin-Elmer spotlight. This system also is a good system for imaging. It has the resolution here is 6.25 micron per pixel, means that it could image a slice of your sample 5 by 5 millimeters for about 7 minutes with such resolution. But if you go now with the other ones, that's Varian. Varian uses, this is a linear MCT array, and that's a focal plane array. The advantage of that is why this area here, it could collect the image in a second instead to be in a minute. Oh, why is that? What's the difference between you have a linear array to collect the image, or you have a focal plane array? Okay. So you have the optical image like this, and then if you have a linear array, what's going to happen is you're going to collect the spectra for each point and shifting this in the space. If you have a focal plane array, you collect the whole spectrum simultaneously. So you have the image in a 20 minutes instead to collect like 5% of the whole image in 20%. So basically that's the difference between linear array and also a focal plane array. Okay? So the focal plane array for imaging is the most efficient and most faster system that is nowadays in the market. So what is the game of resolution? Okay, when you obtain this image. So here I have that's a work done by Peter Lesch in the Robert Koch Institute in Berlin, and this was published a few years ago. So that's the slice of your sample from the colon tissue. Oh, that's why you have the crypt in colon tissue. So that is the slice of colon. And then you want to collect this image and performs your cluster classification or any type of analysis. And how sensitive is the identification of that tissue in terms of resolution? Okay, why that's important? Why I want to do this? Well, how the things works nowadays? You collect biopsy from a patient, you slice it, then you treat it with HE, and then you have diagnosis. That takes time. And also, there are some variability in diagnosis. If you have it automatically by infrared, everything can be done quite fast. And there is no space for misclassification, because what you're looking here is the biochemical changes. It's not morphological changes. So by infrared, to do the diagnosis would be much more efficient and practical than with the pathologist. Don't tell this to them. So if you decrease your resolution, you could see that at some point you cannot distinguish no longer what is colonostomy, what is crypta, or another type of tissue. So bear in mind that this resolution, 12 to 14 micrometer, you still have a good resolution for a morphological and also a biochemical diagnosis if you have this type of a tissue. Okay. Where am I going to place that? Once I do the slice, I should place in a window that does not have infrared active modes. For this, there is a plenty of, we call windows in the market that you could use it. So CAF2 is a good one. It's very suitable for that, although it's a bit expensive. If you buy a slide, let's say this one here, in Germany, you would pay about $150 for a piece. And then if you buy this in England, we would pay about £9 a piece. So buy it in England is much cheaper than buy it in Germany. Okay? So by £9 you could get a slide like this with CAF2 and do the job the same way that we do for corns that sells in Germany. I don't represent the company. I'm not representing it. The other one is a BAF2, zinc selenate, silicon, germanium. There is a plant in the market. But the good point of calcium fluoride is this point here. You can restain it by HA. Means that you use your slides, get your sample on it, image it, compare with the morphological, wash it out, keep using it, wash it out, keep using it until some student break down. Okay? Yeah, I know that happened. And also, please, people that work in a microbiology, that happened in my lab, don't tell to anybody. They get this window, and since they are microbiologists, they have to flame. So what they did is, with $150 window, they flame it. Poof, destroy it. So don't do that. Okay. So let's go to the most interesting point is, okay, I did all this, and well, where am I going to use that? Okay. So let's talk about Raman. So this is work we have done. This was published in 2011, but we have done that in 2009, 2010. The first project proposed that I had, it was for breast cancer diagnosis. Why breast cancer diagnosis? Because it's more intensive here in Brazil, has a very big social impact. So the idea was, okay, let's start it to see if we were able to identify the type of breast cancer in the non-invasive way in the real time. So we did these things for about 4 or 5 years. We analyzed about 1,023 patients. So you got a bunch of big spectra of many different types of cancer. So we have a big database. But that were done in vitro. Means that the sample were collected from the patient, and then you collect this in vitro. But then we decided, okay, this is done. We know already what is different type of cancers in the breast. And let's see now how this is for in vivo. For in vivo, we use the animal model. Okay, we induce breast cancer on those rats, Witzers, by gavage. Witzers, they die before they develop the cancer. So Sprague-Dawley was the best ones. So then we follow up the whole process of cancer formation on this breast of those animals. But then we try to do this transcutaneously, although we know that the laser penetration is not that deeper, and since the skin of the mouse is very thin, we want to determine what is the influence of skin in the diagnosis of these vibrational modes of this cancer. So we collected first with the optical fiber transcutaneously, means the skin is here and the breast is here, the disease is here. And then after that, in the same spot, very carefully, we remove, we rebate, I think you call, we remove the skin, and then we collect again the Raman in the same spot with no skin. And then after that, in the same spot, we biopsy the sample, and then we do Raman again. We did Raman again. So what you see, there are plenty of differences. When you have this on the top of the skin here masks most of the changes that you could detect by the disease. Oh, by the way, that is when we did this. Usually people, well, I forgot to mention this. What I show it, like you have a fingerprint region that's low frequency vibrational modes that goes from like 400 to 1800, and then you have the high frequency modes that goes from 2800 to 3600. So what is the difference between to analyze the fingerprint region or in high wave numbers? Is you are using the optical fiber. The optical fiber is made of fused silica, and fused silica has a Raman signal. So depends how big is the change, the influence of the fiber signal, you mask the effect that you want to see in your modes. So you have to get rid of that, and one way to get rid of that is to probe in the high frequency modes, because in the high frequency there is no signal at all from the optical fiber. So you could use this region to analyze the data and get the diagnosis. Okay, so that's what we have done here, and it's not only to diagnosis here, but if you are more careful looking at it, you could see that when you have the skin, we don't have a very nice sensitivity, neither specificity. When you remove the skin, it got improved, and when you do biopsy tissue, then we did it no mistakes at all. Okay, it was 100%, and that is true. Okay, that's clear. You could see by this PCA plot, that's no misclassification between a cancer and no cancer tissue. Okay, that's not practical because that's what I have done today. So that's not a good techniques to probe these things. Okay. But what's the main reason of that? When you are probing, the main point, and I'm going to show you later, is when you biopsy the sample. When you are probing first, you are probing the whole bulk. Okay, the laser light is penetrating deeper in the tissue, and you get the whole bulk of signal from that. When you biopsy it, you get a slice, you biopsy the sample, then you have a slice. And where the pathologist reads does not necessarily correspond to where you measure, where you shine your laser. And the pathologist no cares if you shine your laser here and the cancer here, the diagnosis is cancer. Okay? So that is one thing that you should be careful when you do this type of study. But besides the diagnosis point of view, you could learn a lot. These different changes here in terms of proteins, in terms of lipids, when these tissue get sick or when the disease starts to progress. Okay, you see that this is a vibrational mode in the water 08 region. You see that for the cancer tissue, you have a lot of hydration of the tissue compared to the normal ones. So now we have to understand why that effect comes from. So besides diagnosis, there are plenty of information on those spectra that people that knows biochemistry could learn and maybe get some clue about the whole progress of this disease. Okay, and maybe this could be related on that region here to this protein called aquaporin, because then Now I have three things to hold it. Now I'm going to get confused. But anyway, that's the point. So it's, I'm going to talk about some diagnosis because that is the topic today. But bear in mind that the whole information, the spectral information that you have there, it's much bigger than just a simple diagnosis. That is an instrument. This was just came in the market. So that's 2012. That's a good point of in vivo Raman application. These people from Singapore, that's all. They just built a system. Well, not just it, but they built a system where they have this 785 laser line excitation, and they measure about 305 patients for this using this system. And the good point about this is that's a Kaiser system. It's another branch that I forgot to mention. And then the 785 laser line, and he used an optical fiber with 200 micrometer diameter, and the spectral resolution is about 9 wave numbers, okay? So the good point of this instrument is the efficiency. You see the integration time is 0.5 second, half second, he could collect a Raman data that appears like this. So once he collected, what he has done, then he built an optical fiber, and he coupled this optical fiber to the endoscope. And now this system is being used in a routine for endoscopic for this gastric cancer diagnosis. That's in Singapore. Okay. So he built also this system, included the whole process of this data. So once you collect the spectra, first of all, if the spectra there is a lot of fluorescence, the data is rejected, collect another one. If there is no fluorescence, but there are some cosmic ray spikes, remove the cosmic ray spike, process the spectra, normalize it, remove the optical fiber signal, process the data, principal component analysis, multivariate analysis, give the diagnosis, online process again. And using this system, he can identify what type of disease this patient has. And from this experiment, he has obtained sensitivity of about 80% and the specificity about 86%. Okay, and don't forget that again, how he does that. Once he probed the region, then the gold standard is histology. He should remove the sample and then do staining and reading the morphological way. Okay, so that is what he has done on 2012, last year, and it's a good example that the Raman for diagnosis start to appear in the market. These people from Vancouver in Canada, they have built also in vivo Raman system where they use it for the skin analysis. So they have a plant, I think they measure about 518 lesions from 453 patients with many different skin diseases, okay, from melanoma to keratosis. So what they have founded here was, again, using 785 laser line, 1 second integration time. So when you think about 1 second integration time, it's really in real-time diagnosis, okay? And then they collect a bunch of spectra, normalize the data, PCA, and then once more, they have this, they compare the malignant with no malignant cancer. So they get it for like skin cancer and pre-cancer, about 90% of sensitivity and 64% of specificity. And for melanoma, from no melanoma, 90% to 64, 90% to 68 for melanoma in keratosis. So it's not there yet. There are some limitations on the Raman system, but this sensitivity and specificity is getting closer from what people has already in terms of histology. Okay, so that is on the way, and don't forget that this field to apply Raman in biological tissue, it started about 15 years ago. It's not that long. So this is a good example from misreading of histology diagnosis. That's a thyroid cancer. Thyroid cancer, it's a very difficult type of cancer to identify because there is not, it's complicated for you collect the sample. You have to do this through PAF. It's a pulsive aspirative needle, and then you collect only a tiny amount of sample. When you collect this tiny amount of sample, the pathologist or the histologist does not have enough material to read it, and always come with follicular carcinoma, no matter what. They could not identify nicely. So to do this diagnosis, they have to go to surgery and detect it, and then identify what type of cancer is that, or kind of lesion is that. So what you have done, we did some study based on this, on this type of cancer, on 2009, and we could got the discrimination here about 72%. But that was a good example from what I told you before. We measured the whole bulk of sample, and when the pathologist sliced it, no matter where we shine the laser, he read the whole tissue, okay, not exactly where we shine it. So now the approach that we are using now is different. We have some collaboration with a medical school. So with the cryo microtomer, they really get the core of the lesion. It's a pure lesion. Then we place it under the microscope, and then we collect the Raman on that point. So very nice Raman spectra. That is about 3-second integration time of this to get this such a nice signal. And this point is marked on the other side of the CAF2 slice. Where we shine the laser is where the histopathologist is going to read it and issue the diagnosis. So with this, we expect to improve it. We expect to improve this discrimination classification. And also, the idea is to have in our database the pure spectra for each type of disease. And then we could compare later on with the bulk, okay? So that's we're still doing this. That was really smart. This is also, that's new, that is 2013, that's this year. Though this guy is also from Singapore, and what they built it was a Raman instrument using like a whole spec. 5 minutes? Okay, skip that. Well, but I want to talk about this. This is a very nice instrument. So what they did, remember I mentioned that you can collect the data in a low wave number and high wave number. So what they did is an instrument that collected simultaneously the low wave number and high wave number. So using this grate, they have this double VP8 grate, volume phase holographic grating, and then one upper part collect the scattering of light in a high wave number, and the down part collect the spectra in the low wave number. So he can have these two spectra simultaneously without changing the grating, and that makes the system much faster and much nicer. Okay, so that's a good example of this instrumentation progress that we have nowadays. Well, that's another application to use Raman imaging, right? That is just example from like a hamster's brain, where you could identify where is the white matter and gray matter and process this using, this image was taken using a VTEC system. Well, let's skip this. That's another example of Raman system in the market. That is very practical for hospital infection. So what they do, the Raman system identify what is the vector contamination. So if a patient has a sepsis process, where this contamination comes from. So you collect the bacteria sample from the door, from the instrument, from the nursery, and then you have your reference, and then you analyze it using this system, and then it traces it back where this infection comes from. And then you could act it to eliminate the infection in the hospital. So that's the instrument also in the market. Skin confocal. That's the area that I'm most involved with now. That's a very nice instrument. I worked like for 10 years with disease. Now I start to work with the beautiful, right? The volunteers that appear in the lab, it's quite nice. So we have to study effect of cosmetic in the aging, effect of a cosmetic in how you call this, Turks? Wrinkles. Okay, so and not only to study the effect of this active, but also to understand what is beyond that. So with the Raman signal, you could collect the data. That is the skin, right? You could collect from the surface to about the epiderm, about 200 micrometer. So you have the whole information, biochemical information. You can determine penetration and also the effect of this. And the whole process takes about 10 minutes to do this type of analysis. So that is very nice field for Raman also, Raman application. And you could use it, 1 minute? You could use also to determine some disease. Okay, that is a dermatite, atopic dermatite, that is the deficiency of NMF content in the skin that comes from because the filaggrin is not breaking down on this NMF content. So you could determine by Raman if the patient or the volunteer has or not a tendency to develop this atopic dermatite. And then you could detect it if he has no allele mutant, 1 or 2 allele mutant. I run out of time, and I'm sorry, but I will stop it here. But let me quick jump. Oh boy, I was going to spend. That's a good point. I mean, just one more extra minute, if you don't mind. That is what I have done that yesterday to know how many publication is the market for in vivo Raman spectroscopy. And then you can see in Raman cancer, you can see that it's a hot topic. You see that it's really growing exponentially here. So it's a good topic for you, and to have a job later on, and also to have a lot of publication. That is São José dos Campos. It's my town. For who does know, it's a technological city where you have the aerospace industry in Brazil. We have the Embraer, is a Brazilian aircraft made that is competing with the Canadian Bombardier, right? And also we have this Vibras, you have INPE, and then you have Campos do Jordão. That's a German-style city in Brazil. That's only 80 kilometers away. And you have also a nice place that's very near, okay? That is the type, we do have many optical instruments in our lab nowadays, about 3 to 4 Raman system, infrared. So all the facility to do a very nice and good research. That is our lab for skin study. It's quite good one, nice, and that is the instrument. And I would like to thank you for your attention, and let's open for the question.
Hi. So, if I work with a fluorescent substance, I use the FT Raman or confocal Raman? What's better?
Well, if you use, it depends of the drug that you're using. But if you use a confocal Raman, it has a good chance to suppress the fluorescence from your sample. If it doesn't, you have to go through the FT Raman.
We don't have more time. If anyone talks with Professor Airton, I prefer that is outside. Thank you.